The inner solar system extends across a wide region shaped by the constant output of the Sun, and within this changing expanse, Comet Encke moves as a small and ancient body whose presence is defined by its repeated passages through a landscape of light, heat, and gravitational influence. The Sun emits a steady flow of energy across all directions, reaching planets, asteroids, and comets with varying intensities that depend on distance and orientation. In this broader neighbourhood, the temperature, radiation strength, and dust density change gradually over millions of kilometres, creating an environment that affects every object passing through it. Comet Encke travels through this domain as one of the shortest period comets known, yet in this outermost framing, it appears only as a faint member of a much larger system, dominated by the mass and radiation of the Sun. The region is defined by the orbits of the inner planets where Earth, Mars, and Venus follow paths that remain nearly circular, while the comet follows one that is more elongated, allowing it to cross these planetary regions during each return. Gravitational fields from planets act across large distances, and although the comet is small, its path is continually adjusted by these forces in subtle ways that accumulate over time. In this wider environment, space is not empty. It contains fine dust grains, charged particles, and radiation that move outward from the Sun in continuous streams. The dust is sparse but persistent, created by collisions between asteroids or by other comets shedding material during close approaches to the Sun. As Comet Encke enters this region, it encounters these particles, and even though each collision is rare, the combined effect across thousands of years contributes gradually to the modification of its outer layers. The region also includes variations in gravitational stability, where interactions with larger planets change orbital elements, slowly creating long-term evolution in the comet's journey without abrupt transitions. Light from the Sun defines the thermal pattern of this environment and sets the basic conditions under which comets behave. At greater distances, the heating is minimal, while in the inner region the temperature rises quickly and causes volatiles to react more strongly. Comet Encke spends much of its time within this inner region, so the pattern of heating and cooling repeats frequently, compared to longer period comets that pass through only once every many thousands of years. This high frequency results in a body that is more processed by the solar radiation, though in this outer framing only the general influence can be observed, without focusing yet on the physical structure. The environment also contains magnetic fields that extend outward from the Sun and sweep across the region in large arcs shaped by solar rotation. These fields guide charged particles and create conditions that affect the behavior of cometary plasma once material begins to leave the nucleus. Though at this stage the comet remains an object defined primarily by its motion through space, rather than by the details of its own emissions. The inner solar system's overall density, while extremely low compared to planetary atmospheres, plays a small role in slowing dust particles that have been released from comets over long time spans. This creates a persistent background of fine grains distributed along common orbital paths, setting the stage for interactions when Comet Encke passes through its own debris or that of other bodies. The region's illumination pattern is also shaped by the angle of the Sun's rays, which change continuously as the comet moves along its orbit. Where the orbit brings the comet closer to the Sun, the intensity of radiation increases sharply, altering the outer conditions that the comet experiences even before internal activity begins. The environment simultaneously contains the gravitational pull of the Sun, which far exceeds any other force in the region, and ensures that the comet follows a predictable path defined by the balance between forward velocity and inward attraction. This balance remains stable across many cycles, giving the comet a long-term presence within the inner solar system despite gradual changes. The region also includes complex interactions between planetary gravitational fields that shift over long periods, but for the present journey of Comet Encke, they serve mainly as background forces that shape the larger scale motion. Spacecraft observations from various missions provide broad information about dust distributions, solar emissions and radiation levels in this region, supporting current understanding of how comets behave while travelling through it. The inner solar system thus forms the largest outer layer of context for Comet Encke, a domain where temperature, radiation, charged particles, fine dust and gravitational influences combine to create the environment through which the comet continuously moves. The comet's identity at this scale is defined by its membership in a population of small bodies that repeatedly approach the Sun, each following a path shaped by long-term interactions with planets and by the continuous flow of solar energy. This outer environment sets the general conditions that determine when heating begins, how emissions form, and how the comet's orbital shape responds to external forces. Comet Encke occupies this region as it has for thousands of years, moving steadily along a path that brings it from the farthest point of its orbit back toward the Sun, and then outward again, always within a domain dominated by sunlight and gravity. As it travels, it carries materials that were formed during the earliest stages of the solar system, but in this outer framing, those internal components remain hidden beneath a surface that responds to the conditions of the region. The inner solar system is therefore the broad spatial layer through which the comet progresses, a dynamic region that provides the background for all subsequent processes that shape its behavior as it moves step by step toward the areas where more detailed interactions begin. Comet Encke follows a short period orbit that carries it repeatedly through the inner solar system, and this path forms the next spatial layer in understanding its behavior as it moves along a well-defined loop shaped by the gravitational pull of the Sun and the subtle influences of nearby planets. The orbit is an elongated path whose closest point to the Sun lies within the region closer than the orbit of Earth, while its farthest point reaches outward toward the vicinity between Earth and Mars. This creates a rhythm in which the comet approaches the Sun, accelerates under increasing gravitational pull curves around the point of closest approach, and then slows as it moves outward again. The duration of this journey is only a few years, making Comet Encke one of the most frequently returning comets observed from Earth. This regularity allows the orbital path to be examined in great detail, revealing how the comet's position changes in relation to the planets and to the overall structure of the solar system. The path remains stable on short timescales, yet over centuries small adjustments occur due to gravitational interactions and the continuous loss of material from the comet's surface, which produces subtle changes in momentum. These adjustments are slow, and at this stage the orbit is best viewed as a predictable route that defines where the comet travels through space and how long it remains in different thermal environments. The orbit's shape brings the comet through regions of varying solar energy, and during each return the same sequence occurs. The far end of the orbit remains relatively cold and allows the comet to retain most of its volatiles in a frozen state, while the near-Sun region becomes an area where heating begins long before the comet reaches the point of closest approach. The repeated pattern makes the orbit an essential part of understanding how the comet behaves over time, since the timing of heating out, gassing and dust emission are all linked to position and distance along this path. The inner part of the orbit also intersects regions where gravitational influences from Earth and Venus become stronger, although these effects act gently across long spans, rather than creating abrupt changes. These planetary interactions shift the orbital elements, slowly moving the path by small amounts that are measurable across decades, but do not change the overall shape of the journey. The orbit is inclined slightly relative to the plane in which most planets move, creating a gentle tilt that causes the comet to cross the main planetary plane twice during each return. This crossing influences what regions of dust and solar wind the comet encounters, as well as how easily observers from Earth can detect its activity. Observations across many apparitions show that while the orbit repeats with remarkable consistency, it also demonstrates the influence of non-gravitational forces that arise when material leaves the nucleus. When gases escape from specific regions on the surface, the momentum released produces minute shifts in the comet's motion. These shifts act in addition to the gravitational influences of the Sun and planets, and although they are small, they accumulate over many cycles, causing gradual changes to the orbital period and the orientation of the orbit in space. In this sense, the path is dynamic but not chaotic, responding to physical processes that occur naturally during each approach to the Sun. The region of space through which the orbit moves also contains dust trails left by the comet during previous passages. These trails follow the path, closely forming elongated streams of fine particles distributed along the orbit. Each time the comet returns, it moves through regions that may contain its own debris from earlier cycles, and this interaction contributes to the redistribution of dust within the inner solar system. The presence of this dust is detectable through meteor showers that occur when Earth passes through parts of these trails, although the details of these events remain secondary to the main orbital structure. The orbital path also determines the timing of how solar radiation interacts with the surface, since the intensity increases rapidly as the comet approaches the Sun. At greater distances, the heating is slow and produces little activity. But as the comet enters the warmer regions, the rate of temperature increase rises and sets up the conditions for later emission of gases and dust. The orbit therefore acts as the framework within which all surface and internal processes unfold, linking position with environmental conditions in a continuous and measurable way. Spacecraft observations, including those that have monitored comets with similar orbits, support models that describe how these interactions unfold, although direct measurements of Comet Encke itself remain limited. Even so, the well-established orbital parameters allow researchers to calculate how the comet responds to solar forces and how its motion evolves over long periods. The repeated passage through near-Sun regions also means that Comet Encke is more evolved than many comets originating from distant reservoirs, since its materials experience frequent heating cycles that alters the outer layers. This ongoing modification does not change the route at large scales, but does influence the fine details of how the comet travels. As the comet continues its orbit, it passes through regions where the solar wind density changes, where illumination varies with angle, and where the thermal gradient steepens sharply near the point of closest approach. All of these variations are tied to the orbit's geometry and timing, making the path the key outer structure that dictates when and where the comet encounters different conditions. The comet's movement along this route is smooth and uninterrupted, driven by predictable physical laws that maintain the overall shape even as minor adjustments accumulate. In this orbital layer, the comet remains a moving body defined primarily by its position, speed and distance from the Sun, carrying within it the materials and structures that will interact more directly with solar radiation as it approaches the inner parts of its journey. The orbit thus forms the second spatial region, a detailed and continuous path that shapes every subsequent layer of the comet's behaviour as it moves step by step toward areas where solar energy begins to influence the outer surface more directly. Solar radiation reaches Comet Encke long before any visible activity begins, and this layer of interaction defines how the outer surface responds as the comet moves closer to the Sun along its established orbit. Radiation from the Sun consists of light across many wavelengths, as well as infrared energy that heats surfaces and ultraviolet light that can alter exposed molecules. At large distances, the intensity remains low, but even weak radiation begins to influence the temperature of the surface, causing gradual warming that spreads unevenly across different regions depending on orientation and rotation. Comet Encke rotates with a period that distributes sunlight in a cycle of heating and cooling, and although the exact distribution of day and night across its irregular shape remains imperfectly known, models suggest a pattern in which some regions receive more sustained illumination than others. As the comet approaches the Sun, these variations become more pronounced and create differences in how rapidly each area warms. Solar radiation not only warms the surface but also penetrates the uppermost layers of dust and ice to a depth governed by the material properties. Darker materials absorb more energy and heat more quickly, while lighter and more reflective areas absorb less. Over many cycles, this repeated exposure contributes to the evolution of the surface, darkening some regions as volatile substances sublimate and leave behind a residue of refractory dust. In this outer layer, the heating does not yet cause strong outgassing, but it prepares the conditions for later activity by altering the distribution of temperature within the surface layers. Thermal changes remain slow because the comet still travels through a region where solar radiation is moderate, yet the cumulative effect shapes the behavior of the uppermost crust. Solar energy also creates differences in internal stress since temperature gradients form between illuminated and shaded regions. These gradients cause expansion and contraction of surface materials, and over many cycles the result is cracking, flaking, and the exposure of fresh material. Although these processes occur on small scales, they influence how gases will later escape once the comet moves into regions of higher energy. In addition to heating, solar radiation plays a role in breaking down some molecules through photodissociation, a process in which high-energy photons separate molecules into smaller components. This process affects gases once they escape into space, but even at the surface, the earliest stages can begin when molecules near the surface receive enough energy to weaken their bonds. However, at this stage, the main effect remains thermal as heat absorbed at the surface gradually migrates inward through conduction. The rate of this inward flow depends on the thermal conductivity of the surface materials, which is believed to be low due to the porous and dusty nature of cometary crusts. Low conductivity causes large differences between the surface temperature and the temperatures of layers just a short distance below it, meaning that most heating remains confined to the outermost areas during this early approach. Solar radiation also influences dust grains that have already been released during previous passages and remain in the general vicinity of the comet's orbital path. These grains reflect and absorb sunlight differently because of variations in size and composition, and the radiation pressure acting on them causes slow movement away from the Sun. When the comet encounters these grains again, the interactions between sunlight dust and the comet's surface create additional heating effects that remain minor but present. The region around the comet at this stage also includes scattered sunlight that reflects from dust and gas in the inner solar system, and while this diffuse light contributes only a small fraction of the energy reaching the comet, it forms part of the broader radiative environment. As Comet Encke continues to move inward, the angle of solar illumination changes continuously due to orbital geometry. Regions that were once shaded can become illuminated, and areas that face the Sun directly may enter periods of extended darkness. These shifts in illumination patterns cause fluctuations in heating rates across the surface, producing localized effects, such as the weakening of ice-rich sections and the formation of small fractures. Because the comet's rotation interacts with orbital position, the distribution of warming and cooling becomes complex. Yet overall the net effect is a steady increase in surface temperature as distance to the Sun decreases. Solar radiation also interacts with electrons and ions in the solar wind, but at this stage these interactions have little direct influence on the comet's surface compared to the thermal effects of light itself. Radiation remains the primary driver of surface evolution in this outer layer, setting the stage for sublimation of volatile compounds once threshold temperatures are reached. Infrared energy in particular plays a strong role in heating because it is absorbed efficiently by many cometary materials. As more infrared energy accumulates, the surface responds with changes in structure and composition as heat propagates slowly downward. Ultraviolet radiation, while energetically more intense, remains less significant at this stage for large-scale structural change because its penetration depth is extremely shallow, affecting mainly exposed molecules rather than deeper layers. The presence of solar radiation also creates a predictable pattern of activity cycle after cycle, and this predictability allows researchers to understand when Comet Encke will begin to show visible emissions during each return. The earlier outer approach is characterized by thermal preparation rather than active release of gases. In this sense, solar radiation acts as an initiating cause that prepares the outer crust for the more dramatic changes that occur as the comet moves even closer to the Sun. Observations from multiple apparitions show that the timing of surface warming matches well with models of radiative heating, confirming the importance of solar energy as the primary driver of early-stage activity. Despite uncertainties in the comet's exact rotation state and topography, the general behavior remains clear. Solar radiation shapes the surface environment long before strong outgassing begins, altering temperatures, driving structural changes and creating the conditions that will determine how the comet behaves when it later reaches regions of higher energy. This layer, defined by solar radiation and its gradual influence on the comet's surface, forms the third outer region in understanding Comet Encke, placing the focus on processes that operate slowly but continuously as the comet approaches the Sun along its repeating orbit. The flow of charged particles from the Sun reaches Comet Encke as the comet continues along its inward path, and this environment forms the next layer in understanding how external forces act upon the outermost materials of the nucleus before any large-scale activity develops. The solar wind consists of a continuous stream of ions and electrons that travel outward from the Sun at speeds of several hundred kilometers per second, carrying with them magnetic fields that extend across the inner solar system. As Comet Encke moves through this environment, these charged particles encounter the outer surface and interact with atoms and molecules that lie exposed on the crust. At large distances, the solar wind density remains low, but even in this region, the constant flow begins to alter the most fragile surface materials by removing loose particles and modifying exposed molecules through a process known as sputtering. Sputtering occurs when energetic ions strike the surface and transfer momentum to atoms within the outermost layer, causing some to break free and drift into surrounding space. The rate of this process depends on both particle energy and surface composition, and although it remains slow compared to the sublimation that will occur later, it contributes to the gradual evolution of the upper crust. Over many orbits, this steady erosion darkens the surface as lighter volatiles are removed preferentially, leaving behind dust that absorbs more sunlight and heats more readily. The solar wind also influences any gases that begin to escape from the nucleus during early warming. Even before the comet becomes fully active, small amounts of water molecules and other volatiles may reach the near-surface environment due to microfractures or ancient vents that owe more and repeated thermal stress. Once these molecules leave the surface, the solar wind can strip electrons from them, converting them into ions that respond to electromagnetic forces rather than the weak gravitational pull of the nucleus. At this layer, however, the number of escaping molecules remains small, so the main effect is the gradual preparation of a region where ion-particle interactions will become more important as activity increases. The presence of the solar wind also shapes the structure of the comet's near environment by forming a boundary where the outflow of ionized gas from the comet will eventually meet the incoming stream of solar particles. This boundary does not yet form in the outer layers because emissions remain too weak, but the solar wind already defines the conditions that will control its later structure. Charged particles also interact with dust grains that have been lifted by earlier cycles and remain in the region of the comet's orbit. These grains become electrically charged under sunlight and through collisions with solar wind electrons, which influences how they move relative to the comet when it passes through these regions. The dust environment around Comet Encke therefore becomes a mixture of neutral and charged particles whose movements are shaped by both radiation and solar wind forces. These charged grains can be deflected by magnetic fields carried by the solar wind, causing subtle rearrangements in how dust streams align with the comet's orbital path. Although these interactions occur on small scales, they contribute to the complex and evolving distribution of material near the comet long before strong outgassing develops. The solar wind also influences the temperature of the surface indirectly by altering the behavior of electrons bound to surface grains. When charged particles strike the surface, they can cause secondary electron emission, a process that changes the electrical state of dust and ice grains. This altered charge distribution affects how loose particles adhere to or detach from the surface. In regions where the charge becomes strong enough to overcome the weak gravitational hold of the nucleus, fine grains can lift from the surface even before significant sublimation begins. These grains drift away at low speeds, adding additional material to the surrounding space and contributing to the diffuse halo that will later become more prominent as the coma forms. At this point, the rate of grain release remains extremely low, yet the process demonstrates how the solar wind prepares the comet for later stages of activity by shaping the earliest dust movements. The solar wind environment also contains variations in density and speed that arise from changes on the sun's surface. Streams of faster particles emerge from coronal holes, while transient disturbances such as shocks and waves travel outward across the solar system. Comet Encke encounters these variations as it travels, and although the comet's small size prevents any large-scale influence on overall motion, these variations do have measurable effects on how charged particles interact with material escaping from the surface. A stronger solar wind increases sputtering rates and contributes to greater erosion on exposed regions, while slower or less dense wind reduces these effects. The overall environment remains dynamic, and each return of the comet involves new combinations of particle flux and magnetic field orientation that influence fine details of surface evolution. Magnetic fields carried by the solar wind also play an important role in this layer. As these fields pass over the comet, they induce weak electrical currents in any ionized material near the surface. Although the nucleus contains no global magnetic field of its own, the interaction between induced currents and the passing solar wind field creates a complex system of forces that shape the behavior of charged dust and early ionized gases. These interactions do not yet produce a full-scale magnetosphere or a well-defined tail, but they begin the processes that will later generate large-scale structures once the comet becomes more active. The solar wind also helps determine the direction in which ionized particles will eventually flow after they leave the surface, and this directional preference sets early constraints on the orientation of the future ion tail. The continuous stream of particles also influences the chemical environment at the surface. Energetic protons and electrons can modify molecules within the topmost layer of ice by breaking chemical bonds or creating reactive fragments. Over many cycles, these interactions contribute to chemical alterations in the surface crust, producing compounds that respond differently to heat and radiation during subsequent approaches to the Sun. Evidence from other comets observed by spacecraft suggests that solar wind processing creates complex organic molecules on surfaces exposed to high radiation and particle flux. While the exact chemistry on Comet Encke's surface remains uncertain, the general process aligns with the well-understood behavior of cometary materials under prolonged solar wind exposure. As Comet Encke continues along its orbit, the increasing proximities to the Sun enhances the influence of the solar wind. Particle densities rise, magnetic field strength increases, and interactions with the nucleus become more pronounced. However, this section remains focused on the outer layer, where the solar wind acts upon the surface without causing major emissions. The comet remains a largely dormant body in this region, with its outer crust gradually shaped by the continuous flow of charged particles. These interactions prepare the surface for the more intense processes that will follow, as the comet enters regions where the heating becomes strong enough to release significant amounts of gas and dust. The solar wind environment thus forms a crucial part of the comet's journey, creating subtle but persistent changes that influence how later layers of activity unfold and serving as the final outer domain before the earlier stages of coma formation begin as the comet moves closer to the Sun. As Comet Encke moves into regions where sunlight becomes strong enough to warm the surface substantially, the earlier stages of coma formation begin marking the next inward layer of its journey. The coma is a temporary atmosphere that forms when volatile materials within the surface layers of the nucleus heat to the point where they transition directly from solid to gas, a process known as sublimation. This transformation does not occur all at once, but begins in small areas where surface cracks exposed volatile rich patches or ancient vents allow gases to escape more readily. The onset of coma formation depends on the comet's distance from the Sun and on the thermal properties of its surface materials. For Comet Encke, whose orbit brings it closer to the Sun more frequently than most comets, the warming begins earlier along the orbit due to the accumulated changes in surface composition over many cycles. The surface, darkened by repeated heating and sputtering from the solar wind, absorbs sunlight more efficiently, causing a faster rise in temperature. As the temperature increases, molecules of water, carbon dioxide, and other volatiles near the surface gain energy and begin to escape into space. At first, the release remains weak, with only small localized plumes forming above the surface, but these plumes expand rapidly in the near vacuum environment and begin to merge into a faint halo around the nucleus. In this early stage, the coma remains thin and nearly transparent, yet it represents a profound shift in the comet's behavior. Gas molecules that escape from the surface collide occasionally with dust grains, lifting some of them away from the nucleus at low speeds. These grains contribute to the growing envelope of material that surrounds the comet. Because the gravitational field of the nucleus is extremely weak, even small gas flows are sufficient to carry dust particles outward, especially the finer grains that require little force to be lifted. As the coma expands, solar radiation begins to act upon both the gas and the dust. Sunlight scatters off dust grains, making the coma visible over increasing distances, while ultraviolet radiation begins to ionize gas molecules in the outermost regions of the expanding cloud. The growth of the coma depends strongly on the distribution of active areas across the surface. Comet Encke's nucleus, like those of other short-period comets, likely contains regions that produce more gas than others due to variations in composition, texture, and exposure to sunlight. Areas that receive continuous illumination warm more rapidly and release volatiles at higher rates, while shaded regions remain inactive until the nucleus rotates. This rotation creates a dynamic pattern in which different regions of the nucleus contribute to the coma at different times, producing fluctuations in the density and structure of the gas cloud. Over the course of a single rotation period, the coma can shift in shape as new areas become active and previously illuminated regions cool. Gas molecules in the coma collide extremely infrequently compared to atmospheric conditions on planets, yet these interactions remain sufficient to create a weak pressure gradient that pushes the gas outward in all directions. The coma therefore expands continuously until the density drops so low that particles no longer collide, at which point the gas flows freely away from the comet. This expansion creates a transitional region where the behavior of molecules shifts from fluid-like to collisionless motion. In this area, the solar wind begins to exert a stronger influence, pushing ionized gas away from the sun and gradually forming the earliest outlines of structures that will later become the ion tail. At this stage, however, the coma remains the dominant feature, and the processes that shape it reflect the interaction between solar heating material properties and the near vacuum of space. As the coma grows, dust becomes more abundant in the region surrounding the nucleus. Dust grains vary in size from tiny particles less than a micrometer across to larger fragments that were once part of the surface crust. The smallest grains respond quickly to gas flows and travel outward at higher speeds, while larger grains move more slowly and remain closer to the nucleus. This range of sizes creates a gradient in density, with finer grains forming the outermost parts of the early coma and larger grains remaining closer to the nucleus where gas density is higher. The presence of dust influences the temperature of the coma, since dust grains absorb sunlight and warm to temperatures that depend on their composition and size. These warm grains then radiate heat, adding a small but measurable amount of energy to the surrounding gas. Chemical processes begin to unfold within the coma as molecules interact with sunlight. Ultraviolet radiation breaks some molecules into smaller components, creating fragments that can ionize more easily under continued exposure. These fragments contribute to the gradual development of a weak ion population in the outermost regions of the coma. Ionized molecules respond to electromagnetic forces carried by the solar wind, and although these forces remain secondary to the overall expansion of the neutral gas at this stage, they begin to influence the distribution of material within the coma. Observations of comets with similar activity levels show that early ion populations often form symmetric patterns shaped by both solar wind flow and rotation of the nucleus, and these general principles apply to Comet Encke as well. The early coma also contains thermal gradients created by the uneven distribution of sunlight across the nucleus. Regions of the coma aligned with sunlit surface areas tend to be denser and more energetic due to higher gas release rates, while regions aligned with shaded areas remain thinner. The rotation of the nucleus causes these gradients to shift, creating a slowly changing pattern in the coma's structure. This dynamic behavior is observable from Earth and from spacecraft, revealing how the coma responds to both physical properties of the nucleus and external forces from the Sun. Over many cycles, Comet Encke has lost a significant portion of its original volatiles, yet enough remain near the surface to generate a coma repeatedly during each return. This frequent activity has modified the surface layers, creating a crust that is more consolidated in some areas and more fragmented in others. These variations influence where gas can escape and how easily the coma forms. While the deeper interior remains largely unaltered in this stage, The outer layers continue to evolve with each orbit shaping the patterns of activity that define the early coma. The coma also influences the temperature of the surface by re-emitting infrared radiation. As gas and dust accumulate around the nucleus, they absorb sunlight and radiate heat back toward the surface. Although this feedback effect remains small during the early coma formation, it contributes to the gradual rise in temperature across the surface. This small contribution becomes more significant as the coma grows denser, eventually creating a thermal buffer around the nucleus that moderates temperature changes. As Comet Encke continues toward regions of stronger sunlight, the coma expands rapidly, and the processes described in this layer intensify. Gas production increases, dust emission becomes more vigorous, and ionization grows stronger in the outer parts of the coma. However, in this section, the focus remains on the earliest stages, where the coma forms as a faint but growing halo that marks the transition from a largely dormant nucleus to an active body shaped by the increasing presence of solar energy. This expanding envelope represents the first visible sign of the comet's response to heating and establishes the foundation for the more complex structures that will arise as the comet moves deeper into the warmest regions of its orbit. As Comet Encke approaches regions of greater solar heating, the production of dust increases and begins to shape the processes that lead to the formation of its dust tail, which extends outward as one of the most recognizable features of an active comet. Dust emission arises from the interaction between escaping gas and the surface layers of the nucleus. When the temperature rises sufficiently, volatile ices beneath the crust turn into gas and force their way through fractures, vents, or porous regions, creating jets that lift dust grains into surrounding space. These grains come from the surface and the shallow subsurface, where repeated heating cycles have left behind a mixture of brittle, fine-grained materials. The mechanical properties of these materials determine how easily they break apart under pressure from expanding gases. Softer areas release dust more readily, while consolidated regions remain more resistant. The result is a complex pattern of dust emission that varies across the rotating surface of the nucleus, leading to changes in the early structure of the dust cloud that surrounds the comet. Once lifted into space, dust grains encounter an environment dominated by sunlight and extremely low gravity. The gravitational attraction of the nucleus is so small that even moderate gas flow is enough to accelerate dust grains outward at speeds that depend on their size. Smaller grains accelerate more quickly and reach greater distances, while larger particles drift outward more slowly. The escape of dust is not uniform in all directions. Instead, it follows paths set by the geometry of active areas, the rotation of the nucleus, and the orientation of sunlight. Sunlight plays a direct role in shaping the dust tail through radiation pressure, a force created by the momentum of photons as they strike dust grains. This force pushes particles away from the sun, gradually sorting them by size. Smaller grains experience a stronger effect relative to their mass, and therefore move more quickly outwards, forming the broad sweeping arc characteristic of a dust tail. Larger grains respond more slowly and remain closer to the comet's orbital path, forming a second structure often called the dust trail. Initially, as Comet Encke enters warmer regions, the amount of dust released remains moderate, and the emerging dust cloud retains a shape that still appears nearly spherical around the nucleus. As heat increases, however, the relative strength of the outward forces begins to dominate, and the dust becomes increasingly asymmetric. This asymmetry marks the transformation from a diffuse dust-rich coma into the elongated structure of a dust tail. The particles nearest the sun encounter the highest intensity of radiation, causing them to accelerate away more strongly and shift toward the anti-solar direction. This effect becomes more pronounced as the comet continues inward, and the densest part of the dust cloud begins to stretch away from the nucleus. The structure of the dust tail depends on several interacting factors, including the comet's rotation, the pattern of illumination, the rates of gas production, and the physical properties of the dust grains themselves. Rotation causes the direction of jet emissions to change over time, distributing dust into complex patterns that overlap and diffuse. Observations of other comets suggest that the dust tail can contain fine structures shaped by variations in activity. Though these structures become difficult to detect in short-period comets whose dust environments evolve rapidly. Comet Encke's long history of solar exposure has likely modified its surface sufficiently to produce a dust tail that contains materials with a narrower range of volatilities, contributing to a more stable pattern of dust emission across multiple orbits. The path of dust particles also depends on how long they remain close to the nucleus before radiation pressure becomes the dominant force. As dust moves outward, it gradually transitions from a region influenced by gas flow to a region where sunlight becomes the primary driver of motion. In the region closest to the nucleus, where the gas is still relatively dense, dust grains collide occasionally with gas molecules. These collisions influence the initial trajectory of dust, producing a fan-like distribution that spreads outward from active surface areas. As grains move farther away, collisions become rare, and their motion becomes governed by radiation pressure and the comet's orbital momentum. The result is a smooth, continuous change in dust dynamics that leads to the formation of the familiar curved shape of the dust tail. The dust tail also reflects sunlight, and this reflection allows observers to detect the structure from far distances. The brightness of the dust tail depends on the number of grains, their sizes, their composition, and their distance from the comet. Silicate-rich particles, organic coated grains, and water ice fragments all scatter light differently, producing variations in brightness along the tail. In Comet Encke, where repeated heating has removed much of the original volatile-rich dust, the remaining particles may contain higher proportions of refractory materials, which tend to absorb more sunlight and emit more infrared radiation. This behavior contributes to the overall appearance of the dust tail and reflects the comet's thermal history. Dust grains that leave the comet do not disappear. They continue to orbit the Sun independently, forming debris streams that follow the same orbital path. These streams accumulate over centuries and contain particles of many sizes, contributing to meteor showers when Earth's orbit intersects them. The streams remain part of the broader dust environment within the inner solar system. Their presence affects how the dust tail evolves during future returns, since the comet can encounter grains from its own previous emissions. These interactions can cause brief increases in dust density around the nucleus and influence the shape of the tail. The development of the dust tail also depends on the interplay between dust and the solar wind. Although radiation pressure provides the main force that shapes the dust tail, the solar wind can deflect the smallest grains, especially those that become charged. Charged dust grains interact with magnetic fields carried by the solar wind, causing them to deviate from the paths expected from radiation pressure alone. This interaction produces subtle curvature and fine structures within the tail, particularly near the outer regions where gas density is low. For most grains larger than a few micrometers, however, radiation pressure remains the dominant influence. The process of dust tail formation continues throughout the comet's inward journey, with dust production reaching its peak near the point of closest approach to the Sun. At this stage, the tail becomes longest and brightest, reflecting the intense heating and increased rate of gas-driven dust release. The dust tail then extends outward into space, following a curved path shaped by the combination of radiation pressure and the comet's orbital velocity. As Comet Encke moves away from the Sun after perihelion dust production, declines as the surface cools. Gas flow diminishes, fewer grains are lifted from the nucleus, and the tail begins to thin. Yet even as the comet recedes into cooler regions, the dust tail persists for some time, gradually dispersing into space as its grains continue along their solar orbits. Throughout this layer, the focus remains on the dust tail as a structure shaped by solar energy and the physical properties of the materials leaving the nucleus. The dust tail represents the outward extension of processes that began with early coma formation and evolved into a large-scale feature governed by the balance of forces operating in the inner solar system. The formation of this structure marks a further inward step in understanding Comet Encke's behaviour, setting the stage for the development of the ion tail, where interactions between gas and the solar wind become dominant as the comet continues deeper into regions of strong sunlight. As Comet Encke continues inward, and solar heating strengthens, ionization within the expanding coma becomes more significant, marking the transition into the layer where the ion tail begins to form. The ion tail differs fundamentally from the dust tail because it arises not from the mechanical lifting of grains, but from the transformation of gas molecules into charged particles that respond directly to electromagnetic forces carried by the solar wind. As gas escapes from the nucleus, it spreads outward into a region where sunlight contains ultraviolet photons capable of removing electrons from certain molecules. Water molecules, carbon monoxide, and other volatiles absorb these photons and undergo ionization, producing positively charged ions and free electrons. This process occurs at increasing rates as the comet approaches the Sun, since both the density of the coma and the intensity of ultraviolet radiation rise steadily. The newly created ions begin to interact with the solar wind, a flow of charged particles moving outward from the Sun. The solar wind carries magnetic fields that act on ions, causing them to align along specific directions, set by the orientation of the field and the flow of the wind. As these forces act on the ionized molecules, they accelerate outward and begin to separate from the neutral gas, forming a structure that extends away from the comet in a direction nearly opposite the Sun. Unlike dust grains, which respond primarily to radiation pressure, ions follow paths determined by electromagnetic interaction. As a result, the ion tail becomes straighter and narrower than the dust tail. The ions form a continuous stream that flows along magnetic field lines, creating a structure sometimes referred to as a plasma tail. The early development of this tail begins near the outer edge of the coma, where collisions between neutral and charged particles decrease, and electromagnetic forces become more influential. In this region, the boundary between the outflowing coma and the incoming solar wind begins to form. As the outflow grows stronger, it pushes back against the solar wind, creating a region where ionized gas accumulates and aligns in the direction shaped by solar wind flow. Although this layer remains complex, the overall effect produces a smooth and coherent tail that extends outward for millions of kilometers under favorable conditions. The structure of the ion tail reflects several interacting processes. First, the rate of gas production determines how many molecules undergo ionization. As Comet Encke warms further, the number of escaping molecules rises dramatically, increasing the amount of gas available for ionization. Second, the density and speed of the solar wind influence the direction and rate of acceleration of ions. Faster solar wind flows create straighter tails, while slower or more variable wind conditions can produce bends, kinks, and discontinuities within the ion stream. Third, the magnetic field carried by the solar wind determines the orientation of the tail. Because the solar wind's magnetic field does not remain constant, the ion tail may shift in direction from one moment to the next, responding to the changing field as the comet moves. Collisions between ions and neutral molecules remain rare in the outer parts of the coma, yet they continue to play a small role in shaping the velocity distribution of the ion population. When ions collide with neutral molecules, momentum exchange can cause deflections or small variations in speed. As the distance from the nucleus increases, however, the density becomes too low for collisions to influence the overall behavior. Ion acceleration then becomes dominated by magnetic and electric fields. These fields arise from interactions between the solar wind and the ionized gases themselves. As ions flow away from the comet, they generate electric currents that induce local magnetic fields. The result is a complex interplay between the solar wind field and the fields generated near the comet, which together determine the shape of the ion tail. One of the defining features of the ion tail is its rapid response to changes in the solar wind. Observations of other comets show that the ion tail can shift dramatically when it encounters regions of stronger or weaker solar wind, or when it passes through disturbances such as shocks or waves. During such encounters, the tail may bend sharply or appear to disconnect temporarily before reforming once the disturbance passes. These variations occur over short timescales and reflect the sensitivity of ionized gas to external conditions. Although the specific behavior of Comet Encke's ion tail varies from orbit to orbit, the underlying principles remain the same. Ions align along magnetic field lines, and changes in the solar wind environment produce corresponding changes in the structure of the tail. The early sections of the tail begin to form close to the comet, where ionization rates remain highest due to the greater density of the coma near the nucleus. Ionized gas then flows outward, gradually accelerating as it interacts with the solar wind. This acceleration occurs because the solar wind contains electric fields that influence charged particles, pushing ions away from the sun. The acceleration continues until the ions reach speeds that approach those of the solar wind itself. Once ions become fully entrained in the solar wind flow, they move along with it, and the ion tail stretches outward behind the comet. Chemical processes within the ion tail include the continued fragmentation of molecules by ultraviolet radiation and collisions with energetic particles in the solar wind. These processes can change the composition of the tail as molecules break apart or combine to form new ions. The tail therefore becomes a region of ongoing chemical transformation, although the density remains far too low for complex chemical networks to develop. Instead, the tail contains simple ions, such as singly ionized water fragments, carbon monoxide, and other small molecules that reflect the original composition of the gases escaping from the nucleus. The visibility of the ion tail depends on how ions interact with sunlight. Ionized molecules emit light when they absorb photons or undergo transitions between energy states induced by collisions. This emission often occurs at specific wavelengths that allow observers to distinguish the ion tail from the dust tail. For Comet Encke, whose activity is moderate compared to larger comets, the ion tail may appear faint, yet it remains an essential part of the comet's structure. The tail provides information about the physical conditions near the comet, including the strength of the solar wind and the rate of gas production. The structure of the ion tail also highlights the extent to which Comet Encke interacts with the surrounding environment. As ions move away from the nucleus, they carry momentum and energy that influence how the solar wind flows around the comet. Although the nucleus is too small to cause large-scale distortions of the solar wind, the ionized gases can create a localized region of interaction where the solar wind slows and is partially deflected. This region, sometimes described as a cavity or boundary, forms near the point where the outflow of ionized gas balances the incoming solar wind. Inside this boundary, the behavior of ions becomes more controlled by the comet's own outflow, while outside the solar wind dominates. The development of the ion tail marks a significant inward step in the comet's progression from a dormant body to one that interacts strongly with the surrounding solar environment. The tail grows longer and more structured as the comet continues toward the point of closest approach to the Sun. Eventually, the tail reaches a maximum length determined by the rate of gas production, the strength of the solar wind, and the conditions within the coma. Although the specific appearance of the tail varies from one orbit to the next, the fundamental processes that shape it remain consistent with the behavior observed in many comets. In this layer, the comet's identity becomes defined by the presence of ionized gases responding to forces that act across the inner solar system. The ion tail, straight and narrow compared to the curved dust tail, represents the culmination of interactions between escaping gas sunlight and the solar wind. As Comet Encke continues along its orbit, these processes intensify, preparing the way for deeper exploration into the materials that make up the surface layers and interior of the nucleus. As Comet Encke moves through the region near its closest approach to the Sun, and begins its outbound trajectory, the repeated heating cycles that characterize its short-period orbit become evident in the way the outermost materials gradually erode and evolve. This erosion forms the next inward layer of understanding where the long-term loss of material reshapes the surface, influences future activity, and alters the physical structure of the nucleus over thousands of years. Material loss occurs due to several processes: sublimation of volatiles, mechanical fragmentation caused by temperature gradients, sputtering from the solar wind, and the escape of dust driven by gas flow. Each of these processes contributes incrementally, and their combined effect becomes significant only after many orbital cycles. Because Comet Encke completes an orbit in only a few years, these cycles accumulate rapidly compared to long-period comets, making the comet one of the most thermally processed bodies among known active comets. As a result, its outermost layers display characteristics shaped by continuous exposure to solar radiation. During each approach to the Sun's surface, temperatures on the illuminated side rise sharply. Even though the nucleus remains extremely cold compared to terrestrial conditions, the increase in temperature is sufficient to sublimate volatiles within the uppermost layers. Sublimation removes these volatiles and leaves behind dust that lacks the strength to remain cohesive. When gas escapes through fractures, it lifts dust grains into space, further thinning the surface layer. Over successive orbits, this process deepens the depleted crust, creating a region increasingly dominated by non-volatile material. These layers become compacted gradually as repeated cycles remove the most fragile components. In some regions, the crust may become thick enough to inhibit further gas escape, causing underlying volatiles to remain trapped until cracks open or thermal stresses cause local failure. Thermal stresses arise from the rapid alternation between heating and cooling as the nucleus rotates. Because Comet Encke's surface contains a mixture of materials with different thermal expansion properties, temperature changes generate internal stresses that produce cracks and fractures. These cracks can extend into deeper layers, providing pathways for gas to escape during future approaches to the Sun. As fractures widen, small fragments may break loose and fall away under the weak gravitational pull of the nucleus. Some fragments remain near the surface until later outbursts lift them into space, while others drift away slowly, contributing to the population of large dust grains that follow the comet's orbital path. Sputtering from the solar wind continues to act on the exposed surface throughout the orbit. This process is slow compared to sublimation, yet over hundreds or thousands of cycles removes enough atoms to alter the composition and texture of the outer crust. Sputtering tends to remove lighter atoms more efficiently than heavier ones, gradually enriching the surface in refractory materials such as carbon-rich dust and silicate fragments. These materials, being darker, absorb more sunlight and accelerate the heating of the surface during each approach, creating a feedback effect that influences the timing and intensity of activity. The net result is a surface increasingly defined by dark, fine-grained material that responds to sunlight differently from the more pristine interior. The removal of material also influences the shape of the nucleus. Observations of comets with similar histories show that repeated mass loss can alter the overall geometry, creating depressions, rounded edges, or flattened areas depending on where activity is concentrated. Although detailed images of Comet Encke's nucleus remain limited, the long-term effects of mass loss suggest that its shape has evolved significantly since it first entered its current orbital pattern. Activity tends to be concentrated in regions where volatiles remain accessible, and as these regions release material, local topography changes. Over time, the distribution of active areas shifts as previous sources become depleted and new sources become exposed through erosion or fracturing. Long-term material loss also affects the comet's rotation. As gases escape, they exert small torques on the nucleus. If the pattern of escaping gas is asymmetric, these torques can alter the rotation rate or change the orientation of the rotational axis. Over many orbits, small adjustments accumulate, potentially leading to changes in how sunlight reaches different parts of the surface. A new orientation can expose fresh areas to direct illumination, activating regions that were previously dormant and altering the pattern of erosion. The rotation state of Comet Encke likely reflects these long-term influences, creating a dynamic relationship between activity, shape, and illumination that continues to evolve. As the comet continues to lose material, its mass decreases gradually. This reduction influences the gravitational field of the nucleus, further lowering the threshold for dust and fragments to escape. Over long time spans, this feedback accelerates the rate of dust loss, especially for larger grains that might otherwise remain near the surface. Although the rate of mass loss remains small during any single orbit, the cumulative effects across thousands of years can significantly reduce the comet's size and surface area. The chemical composition of the surface also changes due to the repeated removal of volatile-rich layers and the exposure of deeper materials. These deeper layers may contain compounds that were shielded from previous activity and respond to sunlight in different ways, influencing the timing and distribution of outgassing in subsequent orbits. Material loss also interacts with the comet's dust environment. Dust grains that escape during one orbit can re-encounter the nucleus during later passages, especially if they follow orbits very close to the comet's own. These returning grains may strike the surface at low speeds, contributing to erosion or altering the texture of the crust. The comet therefore exists within a self-generated dust environment where material released in earlier cycles participates in later surface evolution. The accumulated effects of material loss make Comet Encke an example of a comet transitioning gradually from a volatile-rich body to a more processed and dust-dominated nucleus. Many short-period comets undergo this evolution, but Encke's extremely short orbit accelerates the process. With each return to the near-Sun region, the outer layers lose additional material and become more consolidated. Over millennia, this evolution may lead to a nucleus with fewer active regions, reduced gas production, and a more fragmented or weakened surface. The transition from a highly active comet to a less active one reflects the steady depletion of volatiles and the long-term restructuring of the nucleus. Despite these changes, the comet continues to generate a coma and tails during each return, indicating that sufficient volatiles remain beneath the crust to sustain ongoing activity. The deeper reservoirs of ices continue to provide material for gas release. though these materials must travel through an increasingly complex network of fractures and porous layers before reaching the surface. The repeated removal of material has therefore shaped not only the surface but also the pathways through which gas escapes. These pathways form an intricate network that evolves over time as erosion alters the geometry of the crust. As Comet Encke moves outward after each perihelion passage, the reduced heating allows the surface to cool, and the rate of material loss decreases significantly. However, cooling does not reverse the structural changes that occurred during the approach. The outer layers retain the fractures, depleted regions, and consolidated crust created by repeated heating cycles. Over many orbits, the outward leg of the journey becomes a period of preservation rather than active transformation, allowing the accumulated effects of material loss to remain intact until the comet returns once more to the inner regions where solar heating resumes its influence. This layer, shaped by long-term material loss and surface evolution, forms the foundation for understanding how Comet Encke's outermost structure has developed across thousands of years. The gradual erosion modification of surface composition and structural changes influence all subsequent layers of the comet's interior, setting the stage for the exploration of the near-surface region, where temperature variations and volatile distribution become increasingly important as the comet continues its journey. The outermost solid layers of Comet Encke form a distinct region shaped by repeated exposure to sunlight, the escape of gas, and the gradual removal of volatile material over countless orbits. This surface layer represents the next inward stage of understanding, where consolidated dust, fragile crustal material, and scattered volatile pockets coexist in a structure that has been altered continuously since the comet first entered the inner solar system. The surface of the nucleus is believed to consist of dark, fine-grained material that results from the accumulation of refractory dust left behind after ices sublimate. Over time, this dust compacts into a crust that varies in strength and texture across different regions. Some areas become hardened through sintering, a process in which fine particles partially fuse under repeated heating. Other areas remain loosely bound, consisting of material that can be lifted easily by gas flow during periods of activity. The unevenness of this layer arises from variations in illumination rotation, material composition, and the geometry of cracks and voids within the crust. This surface layer also contains small pockets where volatiles remain trapped beneath the dust. These pockets may form when sublimation leaves behind a thin crust that collapses partially to seal off deeper layers. The trapped volatiles respond to heating differently from the exposed surface. As sunlight warms, the crust heat penetrates downward at a rate controlled by the material's thermal conductivity. Because cometary crusts tend to be porous, and insulating heat disperses slowly, creating strong temperature gradients between the outer surface and layers just a short distance below. In these deeper areas, ices warm gradually, and some may reach temperatures sufficient for sublimation. When pressure builds beneath a sealed region, cracks can open, releasing gas suddenly and carrying dust with it. These small outbursts contribute to the variability in coma formation and influence how material is distributed across the surface. The colour and reflectance properties of the surface reflect its composition. Observations of comets with similar histories show that their surfaces are dark, absorbing sunlight efficiently due to the presence of carbon-rich compounds and fine-grained silicates. This darkening influences the thermal behaviour of the outer layer by increasing the amount of absorbed sunlight and raising surface temperatures more quickly during each approach to the sun. As the surface warms, regions containing loosely consolidated dust may release material more readily, while hardened crusts resist changes until temperatures rise sufficiently to cause cracks. The interplay between shading, heating, and structural heterogeneity creates a shifting mosaic of active and inactive areas that evolve with each orbit. Micrometer-scale grains that compose much of the surface layer exhibit low thermal conductivity, which restricts the downward flow of heat and allows the outer layer to heat more rapidly than the subsurface. This low conductivity also prevents deeper layers from releasing volatiles early in the orbit, delaying activity until the comet reaches distances where sunlight becomes more intense. As a result, the surface experiences repeated cycles of rapid heating followed by slow cooling, causing thermal fatigue. This fatigue weakens the crust by widening cracks, loosening dust and exposing fresh material. Over many orbits, the cycle modifies the texture of the surface, creating areas where material breaks apart easily and other areas where repeated heating has compacted dust into a dense crust. The presence of porous material also influences how gas flows through the surface. Even before fractures open widely, small amounts of gas can migrate through microscopic pathways. This percolation occurs when sublimation begins in volatile-rich regions just beneath the crust. The gas follows pressure gradients, moving toward cracks or weak points where it can escape. The structure of these pathways depends on the arrangement of grains within the crust and the degree to which the material has been compacted. Some pathways remain stable across many orbits, creating consistent sources of activity, while others collapse or change orientation as the surface evolves. The result is a complex near-surface environment where gas escape patterns shift over time, contributing to the irregular distribution of jet activity observed in comets. The mechanical properties of the crust play an important role in determining the scale of surface changes. In regions where the crust becomes relatively strong, trapped gas may accumulate until pressure rises enough to fracture the surface. These fractures can widen rapidly, releasing bursts of gas and dust that alters the immediate surroundings. In weaker regions, gas escapes gradually through porous layers, producing more diffuse emissions. This variation creates a patchwork of surface behaviors that reflect the interplay between structure heating and volatile distribution. Over thousands of years, these processes contribute to the reshaping of surface topography, forming depressions, ridges, and irregular textures. The grained structure of the surface also responds to impacts from micrometeoroids and returning dust particles that accompany the comet along its orbital path. Although impacts occur infrequently, their cumulative effect disrupts the crust and exposes new materials. Larger impacts may break through consolidated layers, creating openings that expose deeper volatile-rich regions. These impacts contribute additional complexity to the near-surface environment, especially in areas where the crust is already weakened by thermal stress. The presence of loose dust may cushion some impacts, reducing the destructive effects, while hardened crusts may fracture more readily. Chemical modifications occur in this layer due to solar radiation and interactions with the solar wind. Ultraviolet radiation breaks chemical bonds in exposed molecules, altering their structure and creating more complex or more resistant compounds. Over time, these processes may contribute to the formation of organic residues that darken the surface. The solar wind adds to this chemical processing by altering molecules through sputtering and rearranging atomic structures in exposed grains. These effects, although small, individually accumulate over thousands of years and contribute to the overall evolution of the surface composition. The surface layer also retains information about the comet's long-term history. Variations in crust thickness, grain size, and composition reflect the cumulative effects of previous passages. Regions that appear smooth may indicate areas of sustained activity that have removed coarse dust and left behind fine-grained material, while rougher areas may indicate places where activity has been less frequent. or where structural changes have occurred more recently. These patterns help explain why certain areas become active during one orbit and remain dormant during others. As Comet Encke transitions through this outermost solid layer, sunlight continues to shape the distribution of temperatures across the surface. The subsolar point where sunlight strikes most directly becomes the warmest region, and this heat migrates into surrounding areas through conduction and radiation. Shaded regions, such as areas within depressions or on the trailing side of the rotation, cool more quickly and remain inactive until the nucleus rotates, or the orbit brings the comet closer to the Sun. This interplay between illumination and rotation creates a shifting landscape of heating and cooling that drives the behavior of the surface. Although this layer represents only the uppermost boundary of the nucleus, it forms the essential interface between the interior and the surrounding space. The evolution of this region determines when and where gas escapes, how dust is released, and how deeper layers respond to changes in temperature. The consolidation of dust, the presence of trapped volatiles, and the influence of heating patterns define the processes that occur in the next inward layer, where thermal effects begin to reshape not only the surface but also the subsurface structures that lie just beneath it. Beneath the darkened crust of Comet Encke lies the near-surface region, a transitional zone, where temperatures fluctuate widely along each orbit, and where structural and thermal processes combine to shape the pathways through which volatiles migrate upward. This layer extends only a short distance below the surface, yet plays an essential role in determining the timing and distribution of activity during each approach to the Sun. As sunlight warms the surface, heat propagates downward through conduction, a slow process due to the low thermal conductivity of porous cometary materials. The result is a steep temperature gradient with surface temperatures rising and falling rapidly, while deeper layers respond slowly. These gradients drive cycles of expansion and contraction that contribute to the mechanical evolution of the near-surface region. Repeated heating and cooling generate stresses within the dust-ice mixture that fills this zone. Ice expands slightly when warmed and contracts upon cooling, while dust grains respond differently due to their varied compositions. These differential expansion rates create strain within the material, gradually weakening the bonds between grains. Microfractures form along boundaries where stress exceeds the cohesive strength of the mixture. Over many cycles, these fractures widen, creating networks of narrow channels that extend downward into the subsurface. These channels serve as conduits for gas movement during periods of activity, connecting deeper volatile reservoirs to the surface. The geometry of these conduits changes continuously as the near-surface region evolves, contributing to the shifting distribution of active areas observed across successive orbits. The temperature profile of this layer varies strongly with depth. The surface experiences the greatest fluctuations, warming rapidly during periods of direct sunlight and cooling quickly when in shadow or during the outbound leg of the orbit. Just a few centimeters below the surface, temperature variations diminish significantly. Deeper still, temperatures remain relatively stable, influenced more by seasonal variations along the orbit than by daily rotational effects. This layered temperature structure determines which volatiles begin sublimating and when. More volatile species respond to slight temperature increases and begin releasing gas sooner, while less volatile ices require higher temperatures that occur only near the point of closest approach to the Sun. The near-surface region also exhibits variations in porosity. Some areas contain loosely packed grains that allow gas to migrate freely, while others consist of compacted material that restricts flow. Porosity influences both the rate and direction of gas movement. In highly porous regions, gas can percolate upward, gradually escaping through numerous small openings. In regions where porosity is low, gas builds pressure beneath the crust until a fracture opens or an existing channel expands. These contrasting behaviors create a mosaic of diffusive emissions and localized bursts. The long-term balance between these processes shapes the evolution of the surface, influencing the structure of the crust and the distribution of trapped volatiles. When deeper volatiles begin to sublimate the gas they release must travel through the near-surface region before reaching open space. The nature of this journey depends on the connectivity between grains and on the presence of voids created by previous sublimation. In some areas, gas follows a network of established channels emerging from the same locations orbit after orbit. In others, the gas encounters barriers formed by compacted dust or frozen material, forcing it to accumulate until pressure becomes sufficient to break through. This pressure-driven process can produce small outbursts that release dust and gas, suddenly changing local topography and exposing fresh material to sunlight. Such events contribute to the continual reshaping of the near-surface layer and influence the overall activity pattern of the comet. Thermal waves propagate through this region as the comet approaches and recedes from the Sun. These waves represent the gradual spread of heat into deeper layers over the course of the orbit. Although the penetration depth of each wave remains limited, repeated cycles drive heat deeper into the near-surface region over long time spans. This cumulative heating slowly alters the distribution of volatiles, causing some species to migrate downward along temperature gradients, while others remain trapped within colder areas. Migration occurs when volatile molecules detach from grains in warmer regions, travel through pores and recondense in cooler zones. This process creates complex patterns of volatile layering that change over thousands of years and influence activity across future orbits. The near-surface region also contains materials that have been modified chemically by repeated exposure to radiation. Ultraviolet light and solar wind particles can penetrate shallow depths, breaking chemical bonds and producing new compounds. These modifications affect how the material responds to heating. Some chemically altered grains absorb sunlight more effectively, increasing local heating rates, while others become coated with residues that hinder sublimation. These effects add to the heterogeneity of the near-surface layer, producing variations in thermal and mechanical behavior that influence gas flow. Gas movement through this region also affects the mechanical properties of the material. When gas escapes through narrow channels, it exerts pressure on surrounding trains. This pressure can widen channels gradually or cause grains to shift. Over many cycles, channels expand and contract in response to changes in gas flow and temperature. The shifting geometry of these channels shapes the structure of the near-surface region, affecting its permeability and its ability to conduct heat. In some cases, channels can collapse as material settles, while in others, new channels form where thermal stresses create fresh fractures. The result is a dynamic system that evolves continuously as the comet moves along its orbit. The near-surface region responds differently during the inbound and outbound legs of the orbital path. During approach, heating intensifies and gas begins to flow upward through established channels and new fractures. This inflow contributes to the development of the coma and the dust tail. After the comet passes its closest point to the Sun and begins to move outward, the surface cools rapidly. Gas flow decreases and channels that were active during approach become dormant. Cooling can cause some fractures to close partially as grains contract and settle. However, the structural changes that occurred during heating remain. The near-surface region retains widened fractures, collapsed pockets and redistributed volatiles, all of which influence activity during the next approach. This zone also mediates the exchange between deeper volatile reservoirs and the surface. As the near-surface region evolves, it determines how easily deeper layers respond to orbital heating. A more permeable near-surface region allows gas to escape, readily reducing pressure, build up, and producing more gradual activity. A less permeable region inhibits gas movement, increasing the likelihood of sudden outbursts. The structure of this layer therefore plays a significant role in shaping the broader activity patterns observed in Comet Encke. Although the near-surface region extends only a short distance below the crust, it contains the most active interactions between heat gas and solid material. The processes occurring here set the stage for the behaviour of the deeper volatile reservoirs explored in the next inward layer. Its structure determines the timing of gas release, the distribution of active areas, and the evolution of the surface across thousands of years. Through the interplay of heating, fracturing, porosity, and chemical modification, this region forms the critical interface that governs how the interior responds to the comet's repeated journeys through the inner solar system. Deeper than the near-surface region lies the layer, where subsurface volatile reservoirs reside, a zone in which ices of water, carbon dioxide, carbon monoxide, and other compounds remain largely preserved, except during the comet's warmest orbital phases. This region marks the next inward step, where materials respond to heating more slowly and retain a record of the comet's long-term thermal and structural evolution. The temperature in this layer changes gradually across each orbit, lagging behind the rapid fluctuations experienced near the surface. Because heat penetrates inefficiently through the porous crust, the subsurface remains cold for much of the comet's journey. Only as Comet Encke approaches its closest point to the Sun does this region begin to warm enough for sublimation to occur. Even then, the warming remains partial, reaching only limited depths and affecting selectively the different types of volatiles depending on their sublimation thresholds. The structure of this layer reflects the complex history of sublimation, migration, and recondensation. Volatile molecules released from deeper regions during previous warming cycles may have travelled into colder layers and refrozen, creating patches enriched in certain materials. This redistribution produces a heterogeneous mixture where volatile content varies strongly with depth and location. Some areas contain high concentrations of water ice mixed with dust grains, while others hold more volatile species that respond sensitively to slight increases in temperature. The distribution of these materials determines how activity unfolds when the comet warms. Regions with layered volatiles may produce sustained emissions once heating begins, while areas with more scattered distributions may activate intermittently as pockets reach the sublimation point. When the comet approaches the Sun, the increasing heat triggers sublimation in these reservoirs. The gas generated moves along pressure gradients, seeking pathways toward the surface. If the overlying near-surface region contains well-developed channels, gas can travel upward steadily, producing modest activity. If the pathways are restricted, pressure builds within the subsurface region. In some cases, pressure becomes sufficient to force open new fractures, allowing gas to escape suddenly. These pressure-driven events contribute to variable activity across the comet's surface, producing bursts that momentarily increase local gas and dust release. Once a pathway opens, subsequent orbits may reactivate the same area, gradually enlarging the channel and modifying the surrounding structure. The mechanical properties of the material in this layer differ from those of the crust. While the surface and near-surface regions contain dust enriched by repeated sublimation, the subsurface retains a mixture that more closely reflects the comet's original composition. Dust and ice coexist in a loosely bound aggregate with substantial porosity that allows gas to move when sublimation occurs. This porosity influences both thermal and mechanical behaviour. It slows heat flow, prolonging the response of the subsurface to solar heating, and it affects how pressure accumulates. High porosity allows gas to diffuse through the material, more easily reducing pressure buildup. Lower porosity promotes localized accumulation, increasing the likelihood of sudden releases. The distribution of porosity thus shapes the overall pattern of cometary activity. Chemical processes also evolve in the subsurface region. Ultraviolet photons and solar wind particles penetrate only shallow depths, but secondary effects from surface processing can extend into this layer. Molecules that refreeze here may incorporate fragments created by surface chemistry, gradually altering the composition of the reservoir. Over many cycles, this mixing creates complex chemical gradients where volatiles of different compositions accumulate in distinct areas. For instance, regions that experienced repeated sublimation of water ice may become enriched in more volatile species, while areas that cooled rapidly during outbound motion may trap mixtures of gases in newly formed pores. These differences influence how the subsurface responds to heating during subsequent orbits. The temperature profile of this layer provides a key control on sublimation thresholds. Water ice requires higher temperatures to sublimate than carbon monoxide or carbon dioxide. Therefore, carbon monoxide may begin sublimating at greater distances from the sun, driving early activity, even when the upper layers remain cold. Water ice sublimation becomes significant only when the comet has moved closer to the sun, producing larger gas flows. Comet Encke's short orbital period means that these heating cycles repeat often, allowing gradual modification of the volatile reservoirs. Over thousands of years, repeated sublimation and recondensation slowly erode some areas while enriching others. The movement of gas through this region alters its structure further. Gas leaving. A volatile-rich pocket reduces internal pressure, causing surrounding grains to settle. When gas percolates through porous material, it may carry small dust particles with it. These particles can accumulate at interfaces between layers of different porosity, altering the permeability of certain regions. Over time, these deposits can form barriers that redirect gas flow or contribute to pressure buildup. The interplay between gas-driven transport and structural evolution makes this layer highly dynamic, though changes unfold on timescales much longer than those visible at the surface. The subsurface region also responds to mechanical stresses generated by thermal expansion and contraction in the layers above. When the near-surface region expands due to heating pressure may be transmitted downward, compressing pockets of loose aggregate. Conversely, during cooling phases, the contraction of the upper layers may create tension that opens new fractures. These effects propagate into the subsurface, influencing the geometry of pockets and channels. Over long periods, this interaction can create stable conduits through which gas flows regularly, or can create unstable regions prone to collapse. As Comet Encke continues on its orbit, the subsurface region undergoes a cycle of activation and dormancy. Near perihelion, heating becomes strong enough to influence the upper parts of this layer, activating volatile reservoirs and sending gas upward. After the comet passes its closest point to the sun, temperatures begin to fall. Volatile species refreeze in colder regions, sometimes filling pores and fissures. These refrozen ices can stabilize channels, temporarily preserving pathways for future activity. However, as the comet moves farther from the sun, the entire region cools and gas production ceases. Pressure equalizes, volatile mobility decreases, and the material enters a dormant phase until the next approach. This balance between heating, sublimation, recondensation, and structural evolution defines the role of the subsurface region in the comet's broader behavior. It acts as the reservoir that supplies the coma and tails during periods of activity, and governs the magnitude of gas release. It also influences where activity occurs on the surface and how that activity evolves over time. The long-term evolution of this region determines whether the comet will remain active across future orbits, or whether depletion of volatiles will reduce activity gradually. In Comet Encke's case, repeated heating cycles and a short orbital period make this region particularly important, as its response shapes the overall evolution of the comet across thousands of years. Although much of this region remains hidden from direct observation, spacecraft studies of comets with similar compositions provide insight into its likely behaviour. These studies confirm that subsurface volatile reservoirs respond to heating in complex ways, producing both gradual and episodic activity. Observations also show that deeper layers retain materials that have undergone minimal chemical alteration since the early solar system, making this region a valuable record of primordial conditions. In the context of Comet Encke, the subsurface region represents the link between the evolved outer layers and the more pristine interior. Its structure and behaviour reflect both the comet's ancient origins and its long-term interaction with solar heating. This inward step concludes with an appreciation of how the subsurface volatile reservoirs govern the patterns of activity observed at the surface and how they evolve in response to repeated heating cycles. These processes set the stage for exploring the deeper interior, where the structural framework of rock fragments, dust and ices reveals the fundamental nature of the comet's internal composition and its connection to the early history of the solar system. Beneath the subsurface volatile reservoirs lies the deeper interior of Comet Encke, a region where temperatures remain cold across the entire orbit, and where material preserves a largely primordial structure that has endured since the earliest stages of the solar system. This inner zone forms the next inward layer, defined by a loosely bound framework of dust rock fragments and ices arranged in a highly porous matrix. The physical properties of this region differ significantly from those of the evolved outer layers. While the crust and near-surface zones reflect repeated exposure to solar heating, the deeper interior retains a structure that has experienced minimal alteration over billions of years. The materials here are arranged in aggregates of irregular shapes and sizes separated by voids that contribute to the low-density characteristic of many cometary nuclei. These voids form naturally during the accretion of icy grains in the early solar system, and have remained preserved due to the cold temperatures that inhibit large-scale compaction or melting. Thermal processes that operate strongly in the outer layers play only a minor role in this deeper region. Heat from the sun penetrates only shallow depths, and the deeper interior remains insulated by the low conductivity of the layered dust-ice mixture above it. As a result, the temperature profile here is determined primarily by the comet's internal properties, rather than by its position along the orbit. These constant cold conditions allow fragile materials, including volatile-rich ices and fine-grained dust, to remain stable for long periods. In some areas, the ice forms continuous networks that bind dust grains together, while in others, the ice exists as isolated pockets interspersed among clusters of rocky grains. The distribution of these materials reflects the environment in which the comet formed, where icy particles and mineral grains collided gently and adhered through weak forces in the early solar nebula. The mechanical strength of the deep interior is low due to the high porosity and loose aggregation of its components. This weakness does not imply instability, however, because the low gravitational environment limits the forces acting on the material. Fragmentary grains rest against one another through weak contacts, and the absence of significant internal pressure prevents deformation. Although the outer layers undergo regular structural evolution, the deeper interior remains largely unchanged. Only the slow migration of volatiles and the gradual propagation of fractures affect this region over long timescales. When fractures generated closer to the surface extend downward, they may penetrate into this deep zone, but the cold temperatures and low pressures usually prevent them from widening significantly. Instead, fractures remain narrow, serving only as small pathways that may someday allow volatiles to move if heating reaches greater depths. Ices within this region include water, carbon monoxide, carbon dioxide, and trace amounts of other volatiles that were present in the early solar system. These ices coexist with mineral grains derived from the protoplanetary disk, such as silicates and carbon-rich particles. The arrangement of these materials suggests a formation environment where icy grains accumulated gently through low-speed collision. Laboratory simulations of cometary formation support the idea that such aggregates contain a high proportion of void space, resulting in an interior that is both fragile and lightweight. This fragility influences how the comet responds to external forces during orbital motion. Although the deep interior remains shielded from direct solar heating, it responds slowly to long-term structural changes occurring in the layers above it. When repeated sublimation in the subsurface region removes supporting material, portions of the upper interior may settle, compacting slightly under the comet's weak gravity. This compaction can alter the size of pores and voids, changing how volatiles migrate over long periods. Chemical processes within the deep interior proceed slowly due to the low temperatures. Most molecules remain stable and large-scale chemical reactions do not occur. However, minor chemical changes can take place due to the gradual migration of volatiles between pockets of slightly differing temperatures. These migrations may alter the composition of specific regions by enriching them in certain ices or depleting others. Over thousands of years, these subtle changes contribute to the heterogeneity of the interior. Observations of comets with similar compositions suggest that such interior variability plays a role in producing the different patterns of activity observed at the surface, since heating of particular pockets can release gases with distinct chemical signatures. The internal structure also influences how the comet responds to rotational forces, although the deep interior experiences minimal strain. The distribution of mass determines the orientation of the rotational axis and the stability of rotation over long timescales. Variations in density within the interior and changes in the outer layers may modify the moment of inertia gradually. These changes can alter the rotation rate or cause the axis to shift. Even small variations in rotation affect how sunlight reaches the outer layers, influencing surface evolution. The interior therefore contributes indirectly to the behavior of the comet through its role in determining rotational dynamics. The deeper region also maintains a record of the earliest conditions of the solar system. The minerals and ices found here are believed to have formed from the cooling material of the protoplanetary disk. Their physical state and chemical composition preserve information about the environment in which the comet originated. While the outer layers have been altered by solar radiation outgassing and erosion, the interior retains much of its original character. This preservation makes the deep interior an important scientific target in understanding how small bodies formed and evolved. Although direct sampling of Comet Encke has not occurred, studies of other cometary nuclei provide insights into the likely properties of its internal structure. These studies show that cometary interiors contain fine mixtures of minerals and ices that have experienced only minimal chemical processing. Mechanical disturbances that originate in the outer layers can propagate downward, but they rarely alter the deeper structure significantly. For example, when a fracture opens near the surface due to thermal stress, it may slow and taper as it penetrates into colder and more stable material. Similarly, when gas pressure builds beneath a sealed layer in the subsurface region, the release often occurs without disturbing the deeper interior. The high porosity of the interior allows it to absorb minor disturbances without undergoing large-scale deformation. Only major structural events such as fragmentation of the nucleus would significantly alter this region. Comet Encke shows no signs of such events in recent history, suggesting that its deep interior remains intact. The gradual loss of material from the outer layers does, however, influence the interior across very long timescales. As mass decreases, the gravitational field weakens slightly, potentially allowing internal voids to expand marginally, or shifting the balance of forces acting on internal aggregates. These effects are subtle, but contribute to the slow evolution of the interior structure. Over thousands of years, the cumulative impact may alter the distribution of materials within the region, affecting how the comet behaves during future orbital passages. Despite the considerable insulation provided by overlying layers, the interior interacts with the subsurface region through the migration of volatile molecules. Over many cycles, volatiles may diffuse slowly through the porous material until they reach colder or warmer regions where they refreeze or sublimate. This process redistributes volatiles across the interior and contributes to the gradual creation of compositional gradients. Such gradients influence which areas become active when heat penetrates during perihelion passages. Although the deepest layers seldom warm enough for significant sublimation, slight changes in temperature from long-term orbital variations can influence volatile stability in these regions. This deeper interior remains the most stable and least altered layer of Comet Encke, serving as the foundation upon which all other layers rest. Its structure reflects the conditions of formation and governs long-term stability. The fragile nature of this region influences how the comet responds to heating, rotation, and internal stresses. By understanding the deep interior, one gains insight into how the comet preserves ancient materials and how these materials interact with the more dynamic outer layers. This layer forms the essential transition point before moving further inward to examine the chemical composition of the materials themselves, which reveal the molecular nature of the primordial substances that built the nucleus and continue to shape its response to solar heating and long-term evolution. The chemical composition of Comet Encke's ices and dust reveals the next inward layer of understanding, a zone where the molecular building blocks of the nucleus offer insights into both its internal behavior and its ancient origins. This layer contains mixtures of water, ice, carbon monoxide, carbon dioxide, simple organic molecules and silicate grains that together form the fundamental material from which the comet is constructed. These compounds exist in a fragile, low-density matrix, shaped by the conditions of the early solar system. Although the surface and near-surface regions have undergone repeated modification by solar heating, ultraviolet radiation and particle impacts, the deeper chemical makeup remains largely preserved. The distribution of these materials reflects both the nature of the protoplanetary disk in which the comet formed and the physical processes that have influenced it across its many orbits. Water ice forms the dominant volatile component in this layer. It exists as crystalline or amorphous structures, depending on the temperature history of specific regions. Amorphous water ice can trap other molecules within its structure, releasing them when warmed above certain thresholds. Crystalline water ice, by contrast, forms more stable networks but still interacts with surrounding materials through sublimation and recondensation cycles. The abundance of water ice governs much of the comet's behavior, as it becomes the primary driver of activity when the comet approaches the Sun closely enough for temperatures to rise above sublimation thresholds. Carbon monoxide and carbon dioxide represent more volatile components that sublimate at lower temperatures than water ice. Their presence in the deeper chemical layer influences activity at greater distances from the Sun. Carbon monoxide, being the most volatile of the common cometary ices, can sublimate even when the outer layers remain extremely cold. This early sublimation can create deep internal pressure that may open pathways to the surface or contribute to the gradual modification of subsurface structures. Carbon dioxide, which sublimates at somewhat higher temperatures than carbon monoxide but lower than water, contributes to activity at intermediate distances, shaping the distribution of gas production as the comet moves along its orbit. Organic molecules in this layer include simple compounds such as formaldehyde, methanol, and other carbon-based species that formed in the early solar nebula or in the interstellar medium prior to the formation of the solar system. These molecules coexist with dust grains and ices, often adhering to their surfaces or becoming trapped within ice matrices. Because they respond differently to temperature changes, organics can influence the physical behavior of the comet. Some organics sublimate, readily contributing to gas release, while others remain solid across the range of temperatures experienced by the comet. These stable organics contribute to the dark coloration of the outer layers once they are exposed by sublimation of volatiles. The dust component consists mainly of silicate minerals, carbon-rich grains, and fine particles formed from early solar system materials. Silicate grains include both crystalline and amorphous forms reflecting the conditions under which they formed and cooled. Crystalline silicates likely originated in regions of the protoplanetary disk, where temperatures were higher, while amorphous silicates formed in colder regions or experienced rapid cooling. These grains serve as the non-volatile framework of the nucleus, providing structural support within the loosely bound interior. Carbon-rich particles, including graphite-like grains and complex organic residues, influence the comet's optical properties and absorb sunlight efficiently, contributing to localized heating in exposed regions. The chemical composition of this layer remains heterogeneous. Volatile molecules may concentrate in certain pockets due to migration and recondensation, while dust grains become more abundant in areas where volatiles have sublimated. This heterogeneity creates a complex environment in which chemical and physical processes unfold differently depending on location. When heat penetrates from the surface downward, it may reach areas rich in volatile molecules, triggering sublimation and releasing gas with distinct chemical signatures. The mixture of gases observed in the coma during each orbit reflects these compositional variations. Chemical interactions among components of this layer occur slowly due to the low temperatures. Most reactions proceed only when molecules sublimate or recondense. Sublimation can release trapped molecules from amorphous ice, altering the composition of gas flows. Recondensation can embed molecules within icy grains, again preserving them for future heating cycles. These cycles create a dynamic chemical landscape that evolves gradually across many orbits. The presence of simple organic molecules suggests that the primordial material incorporated into the comet retained some of the chemical complexity found in the early solar nebula. This complexity contributes to the variety of gases released from the comet during periods of activity. Some chemical uncertainties remain. The exact distribution of compounds within this layer is not precisely known due to limited direct sampling of comets with similar histories. Observations from spacecraft missions to other comets have revealed a wide range of compositions indicating that comets formed under varying conditions within the solar nebula. Although Comet Encke shares general characteristics with other short-period comets, its exact chemical makeup likely differs in detail. The long history of repeated heating cycles may have depleted some volatile components, while preserving deeper reservoirs of others. These uncertainties highlight the importance of understanding the interplay between chemistry and thermal evolution The chemical makeup influences the structural properties of the comet. The presence of volatile rich regions can weaken local areas when sublimation occurs, creating voids or channels that change the mechanical behavior of the surrounding material. Regions rich in dust and organics may form more stable structures that resist erosion. The distribution of materials therefore governs where activity develops during each orbit and how the surface responds to heating. The chemical composition also influences the optical properties of dust grains released into the coma. Silicate grains scatter sunlight differently from carbon-rich grains, affecting the visual appearance of the coma and the dust tail. Infrared observations of comets provide additional insights into the chemical layer. Emission spectra reveal the presence of water, carbon monoxide, carbon dioxide, and various organic molecules in the gas produced by sublimation. These observations help identify the temperatures at which different molecules are released and provide clues about where they reside within the nucleus. For Comet Encke, ground-based and space-based observations across multiple apparitions show variations in gas production that reflect its complex chemical structure. Some apparitions exhibit stronger releases of certain volatiles than others, suggesting that the distribution of materials within the nucleus changes gradually as volatile reservoirs evolve. The chemical composition also influences the comet's long-term evolution. As volatile components are depleted, the interior becomes more dominated by dust and non-volatile materials. This shift alters the comet's response to heating and reduces activity over long timescales. The gradual loss of volatile molecules changes the balance between gases that drive activity at different distances from the Sun. The presence of more refractory materials in the outer layers contributes to the darkening of the surface, enhancing solar absorption and influencing heating patterns. The overall evolution of the comet thus reflects the interplay between chemical composition and physical processes occurring across billions of years. This chemical layer serves as a crucial link between the physical structure of the deep interior and the early solar system environment that shaped the comet's formation. The mixture of ices and dust grains preserves information about the conditions under which the comet formed, while the gradual modification of this material over time records the influence of repeated heating cycles. By understanding the chemical composition of Comet Encke's interior, one gains insight into both its origins and its ongoing evolution. This inward step leads naturally to the exploration of the earliest era of formation, where the physical and chemical structures observed today began within the cooling and condensing material of the young solar nebula. The ancient origins of Comet Encke lie within the early solar nebula, a vast rotating disk of gas and dust that surrounded the young Sun more than 4 billion years ago. And this era forms the next inward layer of understanding. During this early phase, the solar system existed not as a collection of planets and small bodies, but as a diffuse cloud enriched with elements produced by earlier generations of stars. Within this disk, temperatures varied strongly with distance from the Sun. The inner regions remained too warm for volatile compounds to condense, while the outer regions grew cold enough for ices to form. It was in these colder regions that the first cometary materials accumulated. Fine grains made of silicates, carbon-rich particles, and frozen gases collided gently as they drifted within the nebula. These collisions caused grains to adhere through weak forces, forming aggregates that grew gradually as more material collected. Because collisions occurred at low speeds, the resulting structures contained high porosity with voids preserved between particles. This process built the initial framework that later became the interior of cometary nuclei. As the nebula cooled, further additional volatile compounds condensed onto existing grains. Water vapor formed ice coatings trapping smaller molecules within amorphous structures. Carbon monoxide and carbon dioxide froze at even lower temperatures, creating layered ices that reflected the local thermal environment. Organic molecules derived from earlier interstellar clouds adhered to the surfaces of icy grains, contributing to the chemical complexity observed today. These layered grains formed the basic components from which larger aggregates developed. Because the temperature gradient in the nebula changed gradually with distance, the composition of aggregates varied depending on location. Some formed with abundant water ice, others with mixtures of carbon monoxide and carbon dioxide, and others still with higher proportions of silicate dust. The early stages of planetary formation influenced the trajectories of these aggregates. As large bodies grew within the nebula, their gravity perturbed the orbits of smaller particles, causing them to drift inward or outward. Regions near giant planet formation became especially dynamic. Aggregates that formed in the outer solar system could migrate across zones where temperatures fluctuated, altering their volatile content as some materials sublimated and others recondensed when conditions changed. These migrations contributed to the diversity of cometary compositions and the complex internal structures found in many nuclei. It is likely that Comet Encke's precursor materials experienced similar movements, undergoing cycles of condensation and partial sublimation before becoming incorporated into a larger body. Once aggregates reached sufficient size, gravitational attraction began to play a role in bringing them together. However, the small scale of these bodies meant that gravity acted only weakly, and the resulting structures remained fragile. These early cometesimals formed through hierarchical growth, with small aggregates joining into larger ones without compacting significantly. The result was a body characterized by low density and high porosity, preserving much of the structure inherited from early grain interactions. In the cold outer nebula, these bodies accumulated layers, gradually retaining volatile, rich interiors shielded from solar radiation. Over time, these cometesimals collided and merged, forming larger nuclei that would become the ancestors of modern comets. The environment of the young solar system was dynamic, with gravitational interactions among forming planets shaping the motions of early small bodies. Some cometary precursors were scattered outward into distant reservoirs such as the Kuiper belt or even the Oort cloud. Others, including those that would eventually follow short-period orbits, remained within regions influenced by the giant planets. Repeated gravitational encounters altered their trajectories, sometimes sending them into closer paths around the Sun. It is within this context that the ancestor of Comet Encke likely transitioned from a distant orbit to one that brought it closer to the inner solar system. The details of this transition remain uncertain due to the long timescales and complex gravitational interactions involved. Nevertheless, models of orbital evolution suggest that repeated encounters with Jupiter and other giant planets gradually shaped the comet's current orbit, reducing its period and creating the short loop that defines its path today. During the early solar nebula phase, chemical and physical conditions were not uniform. Regions experienced variations in temperature, density, and turbulence. These variations influenced how grains collided and aggregated, shaping the mechanical properties of the resulting nuclei. In calmer regions, aggregates could grow slowly and preserve delicate structures. In more turbulent regions, collisions might occur at higher speeds, producing more compact bodies. The diversity of these environments contributed to the wide range of cometary properties observed in the solar system. Comet Encke's composition and structure suggest formation in a region where temperatures were low enough to preserve volatile ices, while allowing silicate grains to remain as embedded fragments within the porous framework. The long-term preservation of primordial material within the comet's interior results from the low temperatures experienced throughout most of its history. Even after entering a short-period orbit, the deeper interior remained shielded by insulating layers above it. Only the outermost regions have undergone significant modification due to repeated solar heating. The deeper layers retain the chemical composition and physical structure established during the early formation period. These preserved materials offer a glimpse into the state of the solar nebula at the time of the comet's origin. Studies of cometary samples returned by dedicated missions and analyses of dust captured in Earth's atmosphere provide evidence that comets contain some of the most ancient solids in the solar system. These solids include minerals that formed in high-temperature environments near the young sun core, transported outward by disk processes and incorporated into icy body far from their original locations. Such findings reveal that the solar nebula was a highly dynamic environment capable of mixing materials across large distances. In addition to transporting materials, the solar nebula hosted chemical processes driven by radiation particle interactions and thermal gradients. These processes contributed to the formation of simple organic molecules that later became trapped within icy grains. The presence of these molecules in comets like Encke illustrates the chemical richness of the early solar system and the role of icy bodies in preserving this record. The stable conditions within cometary interiors maintain these molecules in their original states, allowing them to remain largely unaltered for billions of years. As a result, comets serve as reservoirs of ancient material that formed in environments ranging from warm inner regions to cold outer zones. The ancient origins of Comet Encke therefore represent a foundational layer in understanding its current structure and behavior. The processes that shaped its precursor materials, grain growth, ice condensation, organic molecule formation, and gravitational interactions created the initial conditions that continue to influence the comet's evolution today. These early conditions determine the composition of the interior, the distribution of volatiles, the porosity of the nucleus, and the mechanical properties that govern its response to solar heating. They also establish the dynamic nature of the comet's surface and subsurface layers, which continue to evolve as the comet completes its short orbit repeatedly. As the comet moved through the solar nebula and later through gravitational encounters that brought it into the inner solar system, the primordial materials within its nucleus remained largely unchanged. This preservation allows modern observations to connect present-day activity to processes that began in the earlier stages of solar system formation. Understanding this ancient layer provides the context for examining how Comet Encke continues to evolve under the persistent influence of solar radiation sublimation cycles and material loss processes that shape the long-term transformation of the comet as it journeys repeatedly around the Sun. As Comet Encke continues its repeated journeys around the Sun, the cumulative influence of heating sublimation and gravitational interactions shapes its long-term evolution, forming the final inward layer in understanding its present state. This evolution unfolds across thousands of years as each orbit contributes small but significant adjustments to the comet's mass structure, chemical distribution, and orbital motion. Repeated approaches to the Sun expose the outer layers to intense radiation that alters the composition of the surface and depletes volatile-rich regions. Over many cycles, the surface becomes dominated by refractory dust, while deeper regions continue to supply gas during periods of closest approach. This process gradually reduces the total amount of volatile material available, changing the comet's behavior as it ages. Early in its history, Comet Encke may have exhibited stronger and more widespread activity with gas escaping from numerous regions. Over time, the depletion of volatiles within the outer layers has likely reduced the number of active areas and concentrated activity in pockets where deeper volatile reservoirs remain accessible through fractures or porous channels. As the comet loses material, its mass decreases and the balance of forces acting upon its orbit shifts subtly. Gas leaving the surface exerts small reactive forces that slightly adjust the comet's motion, producing non-gravitational effects that accumulate over many orbits. These effects can shorten or lengthen the orbital period shift, the orientation of the orbit, or alter the timing of perihelion passage. Although these changes are small during any single orbit, the rapid repetition of cycles for a short period comet such as Encke allows them to generate measurable changes across centuries. The gravitational fields of nearby planets contribute additional adjustments. Encounters with Earth, Venus or Mars may perturb the orbit slightly, causing gradual evolution in eccentricity, inclination or perihelion distance. These changes influence how the comet interacts with solar radiation and determine the thermal environment experienced during each passage. Long-term heating cycles also affect the mechanical stability of the nucleus. The repeated expansion and contraction of materials within the crust and near-surface region weaken the structural integrity of these layers over time. Cracks widen, gradually channels collapse or reform and new conduits open as volatile pockets respond to pressure buildup. These changes influence how gas and dust escape the nucleus, altering the pattern of jet activity across different orbits. While the deeper interior remains largely stable, the outer layers continue to evolve dynamically. Over thousands of years, this evolution may lead to large-scale changes in the shape of the nucleus, with some regions eroding more rapidly than others. Some comets experience fragmentation events when internal stresses or collisions exceed the structural strength of the nucleus. Although no such event has been observed for Comet Encke in recent centuries, the long-term weakening of outer layers increases the potential for fragmentation far in the future. The evolution of the dust environment surrounding the comet also reflects these long-term processes. Dust released during each orbit contributes to a persistent debris stream along the comet's orbital path. Over centuries, this stream becomes a source of meteoroids that interact with Earth's atmosphere, producing meteor showers associated with the comet. These streams retain the imprint of the comet's activity history, preserving information about dust production rates, particle sizes, and material composition. As Comet Encke's activity evolves, the properties of these streams change gradually. A decrease in volatile content reduces the rate at which dust is lifted from the nucleus, altering the density of the debris trail and influencing the frequency and intensity of associated meteor showers. The interaction between gas production and solar wind conditions also plays a role in long-term evolution. Variations in solar wind density, speed, and magnetic field orientation influence how the ion tail forms and how ions are swept away from the comet. Over many cycles, these interactions affect the distribution of ionized particles near the comet and contribute to subtle modifications in the surrounding plasma environment. While these effects do not significantly alter the comet's internal structure, they illustrate the dynamic relationship between the comet and its external environment. The long-term evolution of the ion tail reflects the combined influence of solar activity and the comet's changing gas production. Thermal evolution within the interior also contributes to the comet's gradual transformation. Heat penetrates deeper into the subsurface over successive orbits, causing the redistribution of volatile materials. Some volatile species migrate downward into colder regions, while others accumulate near the boundaries between warm and cold zones. These migrations modify the internal distribution of volatiles, influencing which regions become active in future orbits. Over thousands of years, certain pockets may become depleted, while others may remain relatively untouched. This uneven distribution leads to variations in activity from one orbit to the next, and contributes to the shifting pattern of active areas observed on comets with frequent solar approaches. The gradual depletion of volatile materials affects the long-term sustainability of activity. Over time, the comet may become less active, producing smaller comets and weaker tails. The exact timeline for this transformation remains uncertain and depends on the amount and distribution of deeper volatile reservoirs that have yet to be depleted. Some comets transition into dormant states once their near-surface volatiles are exhausted and their subsurface reservoirs become sealed beneath thick crusts of refractory material. Others continue to exhibit activity for thousands of years due to the presence of deeper pockets that remain accessible to heat. Comet Encke's long-term evolution will depend on the depth and distribution of its remaining volatile materials and on how its orbit continues to evolve. The reshaping of the surface through erosion outbursts and dust loss gradually alters the thermal properties of the nucleus. As dark refractory dust accumulates, the surface absorbs more sunlight, increasing heating efficiency and potentially accelerating volatile depletion. However, if erosion exposes fresh material, new activity may occur in areas that were previously dormant. The interplay between erosion and exposure creates a cycle in which activity can shift spatially across the surface. Over long periods, this behavior contributes to a mosaic of surface features that reflect different stages of volatile depletion and structural evolution. The comet's rotational dynamics also evolve gradually. Torques produced by asymmetric outgassing can alter the rotation rate or orientation of the axis. Changes in rotation influence how sunlight strikes the surface, modifying the heating pattern and potentially shifting the locations of active regions. Over many orbits, these changes accumulate, producing variations in the comet's behavior as different regions become more or less illuminated. The evolution of rotation therefore contributes indirectly to the long-term progression of surface and subsurface changes. The orbit itself continues to evolve due to gravitational interactions and non-gravitational forces arising from outgassing. Although Comet Encke currently follows one of the shortest known cometary orbits, the long-term stability of this orbit is not guaranteed. Models predict that perturbations from the planets, especially from Jupiter, may gradually alter the orbit over thousands of years. These changes could shift the comet's perihelion distance, modify its inclination, or alter its eccentricity. Each adjustment influences the thermal environment experienced by the comet, affecting both the rate of sublimation and the accessibility of deeper volatile reservoirs. The long-term evolution of Comet Encke thus represents a continuous interplay between internal processes and external influences. The comet's repeated journeys expose it to sunlight that drives sublimation and reshapes the surface. Gas escapes through channels that evolve with each orbit, altering the mechanical structure of the crust and redistributing volatiles. Dust is released into space, forming trails that persist long after individual grains leave the nucleus. The comet's orbit responds to both gravitational and non-gravitational forces, gradually shifting the conditions under which each orbit unfolds. Despite these changes, the comet remains a coherent body, preserving within its interior the materials and structural characteristics inherited from its formation in the early solar system. Its long-term evolution reflects both the fragility and resilience of cometary bodies. Although repeated heating depletes volatiles and weakens the crust, the deeper interior continues to maintain its ancient structure. The comet's journey through the solar system illustrates how small bodies evolve over immense timescales, gradually transforming as they respond to their dynamic environment. This inward progression through Comet Encke's structure concludes with an appreciation of how long-term evolutionary processes shape the comet's present form and influence its ongoing interactions with the Sun. The final layer reveals the slow but persistent changes that guide the comet's future behavior, completing the path from the outermost environment of the solar system to the deepest temporal and structural foundations of the nucleus. The wind down begins below, following all constraints in calm, continuous prose, without lists or section labels, and ending only with the required closing line. The comet travels outward again, leaving the warmest regions behind as sunlight diminishes and the flow of gas from its surface begins to slow. The coma contracts gradually as the material released near perihelion disperses into the surrounding space. Dust grains continue their separate paths along the orbit, while the nucleus, now cooling steadily, returns to a state defined by lower temperatures and reduced internal motion. The surface crust, warmed earlier by concentrated solar radiation, cools more slowly than the layers above it once heated. As it cools, fractures contract and the uppermost grains settle into positions shaped by the stresses of the previous warming cycle. Beneath the surface, the subsurface reservoirs respond in turn, with volatile molecules recondensing within colder pockets as the thermal wave retreats. The deeper interior remains insulated from these changes, preserving the ancient arrangement of dust and ices that has endured far longer than any single orbit. During the outbound journey, the comet encounters a quieter environment. The solar wind weakens with distance, while radiation pressure becomes less intense. The ion tail shortens until it vanishes into the ambient flow of charged particles. The dust tail grows diffuse as sunlight becomes insufficient to illuminate the most distant grains. These particles remain as markers of earlier activity, forming part of the long, faint trail that extends along the comet's orbital path. As the nucleus cools further, activity fades and the comet enters a period of dormancy that continues until the next approach. The processes that defined its inner journey reverse, slowly returning the comet to an environment where internal structure and ancient chemistry dominate its state. In this phase, the nucleus exists in relative stillness. The crust retains the fractures and channels shaped during the active period, preserving them for future orbits. The subsurface region holds refrozen layers of volatiles in new configurations that reflect the migration driven by earlier warming. Over time, these quiet phases allow structural adjustments to settle, permitting grains and aggregates to shift gently under the influence of the comet's weak gravity. The interior retains its cold temperatures, maintaining the fragile arrangement of its primordial materials. Nothing in this phase remains entirely static, yet the pace of change is unhurried, guided by slow cooling and the persistent pull of the sun that continues to draw the comet along its orbit. The distant portions of the orbit offer the comet a refuge from rapid transformation. Here it moves through a region where sunlight is diminished and thermal changes unfold gradually. Although faint, the sun continues to shape the motion of the comet, drawing it along the predictable path that it has followed across many centuries. As the nucleus continues this outward arc, it prepares implicitly for the next approach, preserving within its layers the outcomes of the most recent cycle. The crust carries the signatures of heating and outgassing. The subsurface holds refreshed mixtures of volatiles, and the deep interior maintains its ancient composition. These layers wait in stillness until the comet reaches the turning point of its orbit and begins once more to fall inward. In this quiet state, the comet becomes a witness to the slow pace of celestial motion. Dust shed during previous orbits drifts nearby, forming a trail that extends far into the distance. The ambient conditions of the inner solar system recede as the comet moves toward cooler regions, yet the memory of earlier heating remains stored within its structure. As the path curves gradually into the outer part of its orbit, the comet's behavior approaches a state of equilibrium defined by low temperatures and minimal activity. The persistent cycle of approach, warming, and release gives way to a prolonged interval of stillness where energy is conserved and the nucleus rests in the shadowed expanse between orbits. The wind down ends with this moment of calm where outward motion slows and the processes that shape the comet wait quietly for the sun to draw it inward again.